Hello, and welcome to the TI Precisions Lab hands-on experiment covering different techniques for driving the ADC reference input. In this experiment, we compare and contrast how the performance of an ADC is affected by two different references. One reference has an integrated wide bandwidth buffer, and the other reference has a lower bandwidth output. We will look at the system's AC and DC performance with the two different references. In the lab's lecture, we described how the ADC performance is impacted by the bandwidth of the reference buffer. In this experiment, we will look at the difference in performance for an AC and DC input signal. We will also see how sampling rate affects reference settling performance. All measurements will be done on the Precision Plabs-SAR-EVM PDK. Let's get started. For this experiment, we will measure the AC and DC performance of the ADS-8860 with two different references. Both references are low-noise precision references, but the Ref 5050 has a low bandwidth output and the Ref 6050 has a high bandwidth output. Note that the bandwidth refers to the ability of the reference to respond to transients. The reference input of the ADC has significant fast-moving current requirements. In this experiment, we will see that the system using the wide bandwidth reference has better AC and DC performance because the reference can respond to the ADC's rapid transient current requirements. For AC performance, our goal is to get the ADS-8860 to meet datasheet SNR and THD. For DC performance, we look at settling of the reference after startup. Ideally, the reference is fully settled during the first conversion, and the ADC does not have a transient startup error. Notice that channel 1 is connected to the low bandwidth Ref 5050, and channel 2 is connected to the wide bandwidth Ref 6050. Now let's look at a summary of the experiments that we will do. The table summarizes the experiments that we will do throughout this exercise. Your measurements will go under the Measured Results section, and they should be comparable to the example measurements shown at the right. The experiments 1 through 3 are done with the Ref 5050, and experiments 4 through 6 are done with the Ref 6050. The experiments will be done at 3 different sampling rates, and you will see that performance is limited at higher sampling rates for the ADC using the Ref 5050. To test AC performance, we look at the SNR and the THD. And to test DC performance, we will look at the reference settling. Print a copy of this table and fill it out as we progress through the experiments. Let's get started. For this experiment, we will first use channel 1 on the Precision Labs hardware. First, set the jumpers as shown here. Connect the PSI to the Plabs board using the SMA cable, and connect the PHY to the Plabs Channel 1 connector. Finally, connect the USB cables to the computer. Throughout this experiment, we will test different amplifiers. Always be careful to install this amplifier right side up with the label at the bottom of the coupon card. You may pause and connect your hardware. Now, let's start the software by selecting the Precision Labs SAR-EVM icon from the Start, then All Programs menu. Once the software is running, you should notice the green Hardware Connected message at the bottom of the software. Also, if the PSI controls are colored teal, the hardware communications is working. You may pause and get the EVM software started. Now, let's measure the AC performance for the system using the low bandwidth Ref 5050. First, select Spectral Analysis on the Pages menu. Next, make sure the sampling rate is 1 megasamples per second. Next, choose the Mark Harmonics option. This will zoom in on the distortion components once we capture the waveform. Now, enter the amplitude, offset, and frequency into the PSI controls. In this case, the amplitude is near full scale at 4.9 volts. The offset is at half full scale at 2.5 volts, and the frequency is 2 kHz. Press the power button to enable the PSI output. Note that it is colored teal when the output is enabled and red when it is off. Next, press Capture and record the AC performance. When using the ref 5050 at 1 megasamples per second, you can see that the THD is significantly degraded compared to the datasheet specifications. In this example, the THD is negative 91.4 dB, whereas the datasheet specifications is negative 108 dB. Also, you can see in the FFT that the harmonics are quite large. You may pause and measure the AC performance. Here, we will make the same measurement at a sampling rate of 500 kilosamples per second. First, change the sampling rate. Second, press Capture and record the AC performance. No other settings need to be changed. AC performance is improved significantly by reducing the sampling rate. THD is improved from negative 91.4 dB to negative 97.1 dB. Note that it is still not equivalent to the datasheet specification of negative 108 dB. You may pause and measure the AC performance. Here, we will make the same measurement at a sampling rate of 100 kilosamples per second. First, change the sampling rate. Second, press Capture and record the AC performance. The AC performance here is now equivalent to the datasheet specification of negative 108 dB. Further reductions in sampling rate will have little to no effect on performance. You may pause and measure the AC performance. In the previous slide, you noticed that the data converter AC performance improved as sampling rate decreased. This is because the reference has time to fully settle when the sampling rate is decreased. Looking at these graphs, you can see at the top graph the current drawn by the ADC reference input. There is a large, rapid 50 milliamp current transient for each bit decision. Each group of current transients represents one conversion cycle. In this example, we see 3 conversion cycles. The bottom graph shows the reference voltage output. You can see the corresponding transients in the voltage for each current transient. Between each current transient, the reference needs to replenish the charge on the decoupling capacitor and settle to within half of 1 LSB. Increasing the conversion time increases the time between each bit decision and between each conversion cycle. This provides more time to charge the reference capacitors and substantially improves the settling on the reference. Good reference settling will improve the data converter's AC and DC performance. Next, we are going to see how DC performance is impacted by the bandwidth of the reference. To do this, we will alternate between converting and having an idle wait time. For a data converter with a constant DC input, the reference voltage will go through a transient behavior when conversions start and eventually settle to a steady state value after many conversions. If the conversions are paused for an idle period, the reference will recover to its initial state. Then, once the conversions resume, the initial transient behavior will repeat itself. Thus, if you have a system that goes to sleep, when it wakes up and begins converting, there will be a transient on the reference that introduces an error for the initial samples. We will see that the magnitude and length of this transient is minimized when a wide bandwidth reference like the ref 6050 is used. From a practical perspective, this reference settling is an issue in systems that use a sleep mode for power saving. This is because the system measured results will have an error during the initial transient. A similar behavior will also happen in multiplex systems when transitioning from between channels that are at significantly different voltage levels. In this case, the different conversion results from the 2 different channels will cause a significant shift in the ADC reference load current requirement. The shift in load applied to the reference will cause a reference voltage transient similar to the sleep mode case. In this figure, you can see the reference voltage and conversion result. Notice that the conversion result will be the inversion of the reference voltage because a conversion result is calculated by dividing the reference voltage over 2 to the n power. We will measure reference settling by just looking at the conversion results. For this experiment, we will make a few minor changes to the hardware. First, disconnect the SMA cable from the PSI. Next, change the jumper to DC in, and make sure that the voltage jumper is set to 4.9 volts. For this experiment, the AC signal is disconnected and we connect the onboard 4.9 volt DC source. You may pause and change the hardware. Now, we can measure the reference settling for the ref 5050 at 1 megasamples per second. First, set the sampling rate to 1 megasamples per second. Next, set the number of averages to 20. This will take 20 measurements and average them to minimize the noise. Third, set the minimum interset delay to 100 milliseconds. This is just the idle time between each set of 10,000 samples. Fourth, press Start Test. This will take a little time as we're averaging 20 readings. Once this is complete, you will see the reference droop in LSB. This is the magnitude of transient error on the reference. In this case, the error is 10.9 LSB. You can see that most of this happens in the first 500 samples. Pause and measure your reference settling. You can right-click and drag to zoom in on the transient. Now you can see more clearly that this is a normal second-order kind of overshoot and ringing. From this picture, it is clear that you will not get the best accuracy until after 300 samples. You may pause and zoom in on the settling. Now let's look at the reference settling with the sampling rate set to 500 kilosamples per second. First, set the sampling to 500 kilosamples per second. Next, press Start Test. After this test completes, you will see that the reference droop is significantly better for the 500 kilosample case. The droop went from 10.9 LSB to 5.35 LSB. Ideally, we would like this error to be less than 1 LSB. So this is an improvement, but still not ideal. You may pause and measure your settling at 500 kilosamples per second. Now, let's check settling at 100 kilosamples per second. First, set the sampling rate to 100 kilosamples per second. Second, press Start Test. After the test completes, you will see that the reference droop is about 1.4 LSB. Although this isn't perfect, it is pretty close to the goal of less than 1 LSB. Thus, here we can see that the DC performance is also improved by reducing the sampling rate. This reference settling is especially important when a multiplexer is used, as each time the input steps, the reference will have to settle again. We will perform the same set of tests with the ref 6050, and you will see that the droop for this reference is good at the entire range of the sampling rates. You may pause and measure settling at 100 kilosamples per second. Now we are going to switch to another channel. To do this, we need to disconnect power to both the PSI and the PHY board by disconnecting the USB cable. Also, close the software. You can do this by clicking the X in the corner. Now we will switch to channel 2 on the Precision Labs hardware. First, set the jumpers as shown here. Note that we are changing back to an AC input with the jumper settings. Connect the PSI to the Plabs board using the SMA cable, and connect the PHY board to the Plabs Channel 2 connector. Finally, connect the USB cables to the computer. Throughout this experiment, we will test different amplifiers. Always be careful to install this amplifier right side up with the label at the bottom of the coupon card. You may pause now to connect your hardware. Now we can restart the software by selecting the Plabs-SAR-EVM icon from the Start then All Programs menu. Once the software is running, you should notice the green Hardware Connected message at the bottom of the software. Also, if the PSI controls are colored teal, the hardware communication is working. You may pause and get the EVM software started. Now we will repeat the SNR and THD measurements for the Ref 6050. Remember, the Ref 6050 has a wide bandwidth integrated buffer, so we expect the system using this device to have good performance, up to the full 1 megasample per second sampling rate. To perform this test, first select Spectral Analysis under Pages. Next, select the sampling rate. For this test, we will use 1 megasample per second, 500 kilosamples per second, and 100 kilosamples per second sampling rates. Let's start with 1 megasample per second. Next, check the Mark Harmonics checkbox. This will zoom in on the distortion components in the FFT. Next, configure the PSI. Set the amplitude to 4.9 volts, the offset to 2.5 volts, and the frequency to 2 kHz. Finally, press capture and record the AC performance. You may pause and measure SNR and THD at all three sampling rates now. The table to the right compares the SNR and THD specification to the measured performance at the different sampling rates. As expected, the measured performance is very close to the specified performance for all the different sampling rates tested. This is because the wide bandwidth reference in the Ref 6050 settles quickly, allowing for low distortion signal capture. Next, we will look at the DC performance with the Ref 6050. For this experiment, we will make a few minor changes to the hardware. First, disconnect the SMA cable from the PSI. Next, change the jumper to DC in and make sure that the voltage jumper is set to 4.9 volts. For this experiment, the AC signal is disconnected and we connect the onboard 4.9 volt DC source. You may pause and change your hardware now. Here, we will check the reference settling for the Ref 6050 by applying a DC 4.9 volt input and measuring the conversions. When we performed the same experiment using the Ref 5050, the performance was degraded at higher sampling rates. For this experiment, first select Reference Settling under Pages. Next, select the sampling rate. Here we will run the experiment at 1 megasamples per second, 500 kilosamples per second, and 100 kilosamples per second. Let's start with 1 megasamples per second. Next, enter the number of datasets that we will average. As before, this will be 20. Next, set the interset delay to 100 milliseconds. This is the delay between each set of points being measured. Finally, press Start Test and measure the reference droop. The figure shown shows the result for 1 megasample per second. Repeat the experiment for 500 kilosamples and 100 kilosamples. You can pause and measure the droop of all three sampling rates now. The table to the right shows the settling performance for the Ref 6050 system. Ideally, the droop should be less than 1 LSB. As expected, the measured performance is very close to this target droop error. This is because the wide bandwidth reference in the Ref 6050 responds quickly to the transient current requirements and holds the reference voltage constant. Now, let's compare all the measured results. The table summarizes the measured results for all tests in this experiment. Your measured results should be close to the example measurements. Again, note that both the AC and DC performance for the Ref 6050 are good for all the sampling rates, whereas the performance for the Ref 5050 are only good at the lower sampling rates. That concludes the hands-on experiment. I hope this was useful for you. Thanks for your time.